You've heard about the main asteroid belt and the faraway Kuiper belt. But there's a third group of unexplored asteroids that could revolutionize everything we know about the origins of our solar system. For billions of years, Jupiter has been shepherding ancient space rocks in its orbit around the Sun. These Trojan asteroids are pristine time capsules that have witnessed our solar system's entire history, from chaotic beginnings to today's delicate stability. Despite numbering in the thousands, we still haven't seen them up close. But that's all set to change very soon. I'm Alex McColgan, and you're watching our channel The Science Signal. Join me today as we take a closer look at these peculiar relics, what we know about them so far, and what mysteries NASA hopes to untangle with its ambitious Lucy mission, set to bring us face to face with the Trojans for the first time in 2027. And we'll even check out two very special asteroids it has seen up close on its way there. Jupiter's first Trojan was discovered in 1906 by astronomer Max Wolf. He noticed it remained fixed 60 degrees ahead of Jupiter as the planet orbited the Sun. A century earlier, mathematician Joseph Louis Lagrange had theorized that small objects like asteroids could remain stable at specific points in a two-body system. Until Wolf's discovery, Lagrange's prediction had just been a mathematical exercise. But now, scientists had evidence he was right. Now, these gravitationally stable regions bear his name and are known as Lagrange points. Trojan asteroids cluster in two swarms, 160 degrees in front of Jupiter at the L4 point, and 160 degrees behind Jupiter at the L5 point. These asteroids are all named after characters in Homer's Iliad, which tells the story of the Trojan War. L4 asteroids are named after Greek heroes, while L5 asteroids bear the names of Trojan heroes. So the two swarms are known as the Greek camp and Trojan camp. While Neptune, Mars, and Earth have Trojans too, Jupiter's are most numerous, with over 15,000 currently confirmed, and some calculations predicting there could be up to 260,000. But how did they end up there? Why aren't they in the main belt or Kuiper belt, along with the majority of asteroids? To understand that, we have to go back 4 billion years to the origins of our solar system. The most common theory of how the outer solar system came to be is the NICE model. It proposes that the giant planets formed much closer together and to the Sun than their current positions. Surrounding them was an outer disk of icy bodies, asteroids, and planetesimals. Every now and then, a rocky body would interact with the outermost planet's orbit before being scattered inward by the planet's gravity. This in turn moves the planet outwards. The process repeats as the rocky body approaches the next planet to the Sun, and the next, until it finally reaches Jupiter. Jupiter's gravity is so immense, these rocks are sent into highly elliptical orbits, or even ejected from the solar system, while Jupiter moves slightly closer to the Sun. After millions of years of slight shifts in orbital distance, the model predicts something remarkable and sudden happened, throwing the solar system into chaos. About 880 million years after our solar system formed, Jupiter and Saturn entered a dangerous rhythm where Jupiter orbited the Sun twice for every one orbit by Saturn. This is known as a 2:1 orbital resonance, and it caused a sharp instability in the orbits of all the gas giants. This instability pushed Neptune, Uranus, and Saturn further out from the Sun, drove Neptune out past the orbit of Uranus, and pulled Jupiter violently closer to the Sun, also known as the jumping Jupiter theory. Meanwhile, the neat disk of planetesimals that had orbited the Sun together for eons were flung in all directions, some toward the Sun, some outward to deep space. Some of these ancient rocks became trapped in Jupiter's stable Lagrange points, becoming the Trojans we see today. Newer theories suggest the Trojans might have been captured by giant planets falling out of resonance rather than into it. If this model is correct, the Trojans aren't just random space rocks, they're preserved samples of the very material that built our giant planets. They could be similar in composition to objects in the distant Kuiper belt, containing pristine material that has remained largely unchanged since the solar system's formation 4.5 billion years ago. Rocks bombarding into each other might sound like a destructive way to build a planet. But those pristine materials are actually vital components of the structures we see. It's thought that asteroids bombarding Earth are a prominent source of the planet's water, hydrating its geology. Which is ironic, because geology, the sponsor of today's video, is now doing the hydrating. Geology's proven ingredients bring all the crucial elements we on Earth need for our skin and hair to flourish. Much like asteroids help moisturize planets, only without the bombardment. Geology creates a unique skincare plan customized to you, which is really cool. And the results speak for themselves. Geology so impressed those who used their 41x award-winning products that they gave it over 10,000 5-star reviews. Whatever you're looking for, body washes, deodorants, or ways to fight off those wrinkles or tired eyes, scan my QR code or follow my link in the description and pinned comment below to see what geology can do for you. And those of you who use my code ASTROM100 at checkout will get 100% off their personalized skincare trial set, plus a free gift, and up to 50% off on add-ons. So far, our understanding of Trojans has been limited to telescopic observations on Earth and in orbit. We think most range from a few kilometers to over 200 kilometers in diameter. But we don't really know for sure. To estimate their sizes, scientists have to assume a specific albedo value which we don't have yet. So it's possible our predictions are way off. We also know they have porous surfaces containing several fine particle silicates, which support the theory that these rocks are primordial and originated in the Kuiper Belt. Still, several questions about this diverse group of primordial rocks remain. How old are they, really? What is their precise composition? Do they harbor ice, minerals, organic compounds? What are their masses and densities like? What goes on under the surface? Do they have any craters? Could Trojan asteroids have rings or satellites of their own? That's why in 2021, NASA launched one of the most ambitious missions in solar system exploration history. A 12-year odyssey, the Lucy mission will fly by a record-breaking 11 asteroids, including 3 main belt asteroids, 5 Trojans, and 3 of their satellites, to answer our burning questions about these mysterious space rocks. On October 16, 2021, the Lucy spacecraft lifted off from Cape Canaveral aboard an Atlas 5401 rocket, beginning a journey so complex and far-reaching that it seems almost impossible. Named after the famous hominin fossil that revolutionized our understanding of human evolution, Lucy aims to do the same for our cosmic origins. Over 12 years, Lucy will make 3.5 giant loops around the Sun, visiting both the L4 and L5 swarms of Jupiter's Trojan asteroids, the first to ever do so. To reach its targets, Lucy relied on multiple gravity assists from Earth. The spacecraft first swung past Earth in October 2022, gaining momentum and adjusting its trajectory. It flew by the asteroid Dinkinish in late 2023, then flew by Earth again in late 2024. This slingshot set it on course to fly by Donald Johanson, a main belt asteroid, in April 2025. From there, its new trajectory put it on course to reach Jupiter's L4 Trojan swarm by 2027. Once there, Lucy will visit 4 Trojan asteroids between 2027 and 2028, Euripides, Polymele, Lucas, and Orus, which will set it on a path back to Earth, making Lucy the first spacecraft to return to near-Earth orbit from the outer solar system. After a third and final assist from Earth in 2030, Lucy will be catapulted toward Jupiter's L5 Trojan swarm, where it will encounter asteroids Patroclus and Menoetius in 2033. Lucy carries 3 key instruments to help it study the asteroids in never-before-seen detail. Ralph combines a multispectral camera and an infrared spectrometer to analyze surface composition. The long-range reconnaissance imager captures high-resolution details, while the thermal emission spectrometer will measure thermal properties of the surface. Lucy is also kitted out with a high-gain antenna to communicate with Earth. By measuring the Doppler shift in these radio waves returning to Earth, scientists will be able to determine how much gravity, and therefore mass, each asteroid has. And so far, the mission hasn't been without its challenges. Shortly after launch, one of Lucy's massive solar arrays failed to fully deploy and latch. These arrays are critical for powering the spacecraft in the dim outer solar system. Encountering an anomaly like this puts the whole mission at risk. Luckily, through months of careful analysis and ingenuity, the flight operations team managed to address the issue, saving Lucy and allowing her to continue on her journey, which I have done a more in-depth video about here. While we're still a couple of years out from the Trojan targets, Lucy has already given us our first taste of discovery. In November 2023, Lucy made its first asteroid encounter, flying past the smallest main belt asteroid ever visited by a spacecraft, Dinkinesh. What scientists expected to be a routine calibration flyby turned into something extraordinary when Dinkinesh revealed two big surprises. First, it was discovered to have a previously unknown satellite, Selam. And secondly, Selam turned out to be a contact binary asteroid, meaning it's made up of two separate bodies that touch each other, probably formed when two asteroids gently collided and fused together. That's what gives it its peanut-like shape. This is a big deal because Selam is the first contact binary satellite ever directly observed. Lucy's initial observations showed that Dinkinesh resembles the near-Earth asteroids Ryugu and Bennu, allowing scientists to compare similar bodies in different parts of the solar system. In April 2025, Lucy completed its second asteroid flyby. This time, it soared within 960 kilometers of a 150-million-year-old main belt asteroid, Donald Johanson. Formed when two smaller bodies collided, Donald Johanson proved to have a strikingly complicated geology, according to NASA. It is also larger than originally estimated, measuring 8 kilometers long and 3.5 kilometers wide. At the time of writing, NASA is still analyzing data from Lucy's spectroscopers that will provide more insight into this asteroid binary. But these main belt findings are more of a bonus than the mission's bread and butter. Like the Dinkinesh flyby before it, this was a systems test for the true mission to the Trojan asteroids. Lucy's mission is particularly exciting because it might resolve a recent discovery that left astronomers perplexed. Astronomers assumed for years that each swarm would have uniform composition, but spectroscopic analysis revealed the opposite. Not only do the Greek and Trojan camps differ from each other, but within each camp, there's remarkable diversity in color and reflectivity. Astronomers have identified distinct red and less red spectral groups among the Trojans, similar to D-type and P-type asteroids. Their albedos range from extremely dark to moderately reflective, and their color variations suggest dramatically different surface compositions. Perhaps most surprising is the discovery of the Euripides family in the L4 swarm, which appears completely anomalous compared to other Trojans. This diversity hints that Trojans formed in different regions before Jupiter captured them. Lucy may confirm they're essentially a cosmic sample platter, materials from across the early solar system gathered in one accessible location. This would revolutionize our understanding of how materials were distributed during our solar system's formation, and potentially explain how Earth acquired the necessary building blocks for life. In an age of instant gratification, Lucy asks us to do something radical. Wait. When Lucy arrives at the Trojans in 2027, it will begin a 5-year exploration that won't be complete until 2033. In this time, the gradual influx of new information could trigger a Voyager-esque anticipation in the public for what breakthroughs may emerge. Still, the real work begins after the mission ends. Students who were in elementary school during launch could be analyzing the mission's findings as graduate students. Space exploration is a multi-generational commitment. But as they say, good things require patience. And this mission is no exception. For now, all we can do is wait. Thanks for watching. If you enjoyed this video, you might want to check out my other videos on asteroids like this one. All the best, and see you next time.